Hi, this is Mrs. Bustamante. We've been talking about phase changes and states of matter, and so I just want to talk about a couple more terms in this video. The first I want to talk about is the heat of vaporization, and we're going to use this graph over here a lot when we're talking about these because we're going to talk about the heating curve, particularly of water, just because we're so familiar with it. And so boiling and condensation we know happen at the same temperature, and that'd be going from a gas to a liquid. And we measure that in the amount of joules or the amount of energy. And oftentimes we talk about that in heat energy. So when we're talking about phase changes, we talk about adding heat, but really we're adding energy. We call the heat of vaporization is just the energy absorbed to turn 1 kilogram of a liquid back into a water vapor, or how much is released to turn it back into a liquid. So that's really like our boiling point is kind of our heat of vaporization point. And it brings me to a good point. This is for water, right? And let's just talk about going from liquid water to gas, right? To water vapor. And we know that water boils, you can heat it up, right? We do that a lot when we cook. So why is it a flat line here? Well, it's a flat line here because when we're boiling a substance, the temperature doesn't actually go up or down in those moments. The temperature remains the same. And why is that? Well, the temperature remains constant here because instead of increasing the temperature of the substance itself, we're actually breaking or making bonds. When we're increasing temperature, we're going to break those bonds so that it can move to the next state. And when we think about it, liquids tend to have slower moving particles that are more organized than gases where they're less organized and have more energy, hence more heat. So why does steam burn more than water? Well, when we think about it, steam is actually gaseous water, where liquid water will be a liquid, right? So it has less energy than it does when it's a gas. We can also use the same graph to talk about something called the heat of fusion, or the energy needed to absorb 1 kilogram of a solid substance into a liquid, right? So to change from a solid into a liquid or a liquid back into a solid, kind of like our melting point, right, when we think about it. And it's the same idea, right? When something melts, when it goes from, say, a crystal structure to a liquid structure, we have to have enough energy that we add into those bonds to break those bonds. And it has to have enough energy before it can actually be in that liquid state. So we'll notice that the temperature remains constant for a pretty good amount of time when we're going through a phase change. Vice versa, as we freeze something, atoms move closer together, they line up, they typically form an organized structure, right? And have less energy. And then lastly, I want to talk about vapor pressure and boiling. Vapor pressure is just molecules evaporating and colliding with the container. And we measure this when it's in a closed system, right? Because otherwise those gaseous molecules will escape. We say that liquids that can evaporate really easily have a high vapor pressure, meaning they're really likely to evaporate because they have more molecules and more collisions and they can gain energy quicker. Liquids that evaporate at higher temperatures, meaning you have to increase the temperature or increase the energy more, have low vapor pressures, less molecules, and less pressure. And so what's boiling? Boiling is really just evaporation that's sped up by temperature or sped up by heat energy, right? We're increasing that natural process by adding energy to make it go faster.